Hello, everyone. This is Shauna coming to you once again with your weekly tutor check-in for this week. This is week 5, and you're going to be doing more probability this week in your 112 class. And this chapter traditionally is a little bit more difficult for students. So you'll notice that you have a little bit of extra time to complete it, but please try to stay up with the syllabus and please try to complete your assignments on time. It is a lot of work in this class, and if you don't complete your assignments on time, not only are you staying up late, um, hurting yourself by limiting the time that we can spend replying to you. So just try to keep up. If you're falling behind, please do get some help. I'm going to try something a little different this week. Instead of merely going through some of the slides and hitting some of the key points, which I'm still going to hit some key points, but I pulled some problems this week, one from section 4.2, 2 problems from section 4.3, and 1 problem from section 4.4 that I hope will illustrate the major principles of the section. And I hope that they'll help you. They tend to be some of the problems that students get stuck on. So I hope this video will help you. And without waiting for too much more, let's get into it. To share my screen this time. And as you see, the first section in 4.2 deals with what we call the addition rules for probability. And the biggest thing you have to remember about this is whether groups are what we call mutually exclusive or not. Mutually exclusive groups means that no members of one group are also members of another group. So a particular person or element is only a member of one group. They're mutually, meaning related to each other, they're mutually excluded from each other. So they don't share any members here. Let's take a look at an example and how this applies. So this is an actual homework problem, and it reads, the number of multiple births in the United States for a recent year indicated that there were 128,665 sets of twins, 7,110 sets of triplets, 468 sets of quadruplets, and 85 sets of quintuplets. Choose one set of siblings at random. Now, before we get to the actual questions, I want to break this down a little bit for you because sometimes this terminology gets a little bit hard. So twins, that's 2 babies born at once. Triplets is 3 babies born at once. Quadruplets is 4 babies born at once. Quintuplets are 5 babies born at once. And this word sets of twins, sets of triplets, sets of quadruplets, and sets of quintuplets are going to matter a lot to you. Sets is going to mean a lot. So as you see further down, I've computed for you the number of sets that we have. So I just took the information that they gave me, and you see that the total number of sets is 136,328. Now, we don't know sets of what. This is where we lose information. But as far as the total number of babies go, I have to multiply the number of sets by the number of babies in the set and then add up those results, which I've done for you here. So the total number of sets is 136,328. The actual total number of individual babies is 280,957. And if you want a copy of these notes when I'm done or when you're watching the video, message me or message Professor Nick Dell and we can provide them for you. So the first question is, find the probability that the pair or the set that you chose is represented more than two babies. You're choosing, remember that's back up, it said choose one set of siblings at random. So in part A, we want to find the probability that it represented more than two babies. So the number of sets of more than two babies plus, over the total number of sets. Remember here, if it's more than two, we're not including the twins. We're not including the sets of two babies. So if you just add the sets of triplets, the sets of quadruplets, the sets of quintuplets, and divide by the total number of sets, you get the result you see on your screen, 7,663 over 136,328, which leaves us with a decimal of 0.0562 and as a percentage of 5.62%. B is similar. This asks about the probability that you had quadruplets, quads, or quintuplets, quints. Now, this is what I wanted to bring up about mutually exclusive events. If you have a set of babies and they happen to be a set of quads, you've had 4 babies at a time. There's another mother down the hall, she had a set of quintuplets. None of those babies that are part of the quads are part of the quintuplets. So these are mutually exclusive groups, and that has a bearing on your addition rule. So when you're looking at the slides, be sure and look at the difference between the addition rule for mutually exclusive events versus the addition rule for non-mutually exclusive events. Non-mutually exclusive events overlap. So once again, the probability of quads plus the probability of quints. We have 468 plus 85 over the total, 136,328 is equal to 553 over 136,328, which when you do the math works out to 0.0041 or 0.41%. Now, you might have been able to get through those. Sometimes people have a little bit of a difficult time with the third one. The third one says choose one baby from these births, not a set. So you're not choosing a set of siblings. You're choosing one baby from that. So in this case, we're not looking at the total number of sets, which is 136,328. We're looking at the total number of babies, which is 280,957. So be careful with that. And you do the math. And when you do the math, you get 21,330. That's how many babies were part of a triplet over the total number of babies born, 280,957. And that decimal is 0.0759 approximately, and that's about 7.59%. So we're paying attention here to mutually exclusive events, whether they overlap or not. These are not overlapping. Now, the next section that you're going to be dealing with deals with a lot of topics. It deals with making tree diagrams, which is an organizational technique. You're going to do that in 4.2, and it's going to continue in 4.3, it deals with different kinds of probability. So in this case, we deal with multiplication rule, and we deal with what we call independent events, dependent events, and we also have conditional probability. So 4.3 is a tough section. It has about 4 or 5 major concepts in there, and I'm trying to highlight a couple of those. This is a problem that we get questions on every semester, and it is from your homework. So it says this: in 2010, about 69.6% of full-time law enforcement workers were sworn officers, and of these, 88.2% were male. Females, however, make up 60.8% of civilian employees. Choose one law enforcement officer at random and find the following. Now, I'm going to come back here for a minute and say that in a lot of these problems, you have tree diagram structures, and I know those can be tricky to draw. There's lots of examples on the slides and in the PowerPoints. I did draw a tree diagram. I draw mine horizontally. I just find that easier, but it is possible to save space by drawing them vertically. You'll see what I did in my problem. Let me go back to that. So we have sworn officers and we have civilian employees. Civilian employees are the ones that support the police officers. They work for the police, but they're not necessarily, necessarily carrying weapons or walking the beat. They're not beat cops. They're civilian employees, okay? So it says choose one law enforcement officer. And for the sake of this conversation, law enforcement officers include sworn officers and civilian employees. So we're talking about one law enforcement worker, okay? So the first question says the probability that she is a female sworn officer. Female sworn officer. So I'm going to skip this part in the middle and go down temporarily to my tree diagram and show you what's going on with that. So here I have a dot, and how far in your dot goes on the page depends on how big your tree diagram is going to be. But you see here that we have two kinds of employees, sworn officers and civilians. So they are on separate branches. They give us the percentage of sworn officers, 69.6%. That was given to us. Now, anytime you're on a pair of branches like this, you have two choices, sworn and civilian. You may have more than two, but this situation has two. We're going to see another problem where the setup is a little different. But they have to add up to 100% of the employees. So if we have 0.696 here, the way we figure out what percentage are civilians is to do 1 or 100% minus that. This is called the complement of the event. And that's another thing that you should pay attention to. Complements are very, very powerful, and use them a lot in 4.3. I could have chosen any number of problems for this. I just picked some that tend to stump people. So again, let's go back to our information here. So 69.6% of all full-time law enforcement workers were sworn, and of those, who's those? Of the sworn officers, 88.2% were male. So here's what's going on. We have 69.6% of the entire workforce is sworn, And from those sworn officer group at the top, 88.2% of those were male. So guess what? The other one minus 88.2 or 0.882 were female, and that was about 0.118, okay? And then it says that of civilian employees, however, let's go back up here. Females, however, make up 60.8% of civilian employees. Choose one law enforcement officer at random. So 60.8% of the civilian officers were female. You could have put female up here and male down here, as long as you put the percentages in the right place. But when you finish, you should have percentages on every branch, and the sum of the probabilities on the branches in the same layer should equal 1 or 100%. So 69.6% plus 30.4% equals 1. 88.2% plus 11.8% equals 1. 39.2 and 60.08 equal 1. Okay? Now that you have that, it's relatively straightforward to apply the probability rules and answer this question. So it says the probability that she is a female sworn officer. So sorry about that. Had a temporary internet glitch there. As I was saying, when we were calculating our female sworn officers, we take 0.696 and we multiply that by 0.118, and we get 0.082 or about 8.2%. The second question, the second part says the probability that this person is a male civilian employee. So here we want to go down to the civilian employees, and we want to go to civilian and male. So we have 0.304 and 0.392, and that gives us, but now here's the problem. This situation here, you have to think about, we talked about mutually exclusive events. Here, if I count all the males, these are all males. Yes, there's my male civilian population, but the population down here is just civilian. So this will give me my civilian males. The third part of this question is the probability that the person is male or a civilian employee. And or are another thing to pay attention to. And means you're looking for the intersection of two groups, male and civilian, female and sworn. Or means you could be part of one or the other or both. So here, the probability that he or she is male or a civilian employee. So we're going to take all the males, and remember, males are in two groups because they're male sworn here and civilian male here. You're going to add the civilian employees, the whole group, but you don't want to double count the males who are civilians, because what's happening is you counted all the males, then you counted all the civilian employees, and they overlap at male civilians. So you're taking out the overlap, and we end up with 0.696 times 0.882, which is the male sworn officers, 0.304 times 0.392, which is the civilian male population, and then we're removing the male civilian population to get our final answer, which is 91.8%. Okay, so that's a little bit about that. And one thing I want to show you here is, here's another problem from that same section with some of the same kind of constraints, and we have a much more extensive tree diagram than we did on the last one. So I'm going to go ahead and read that problem, and then I'm going to do some preliminary analysis, and then we're going to see what we can see about this. So this says, in a recent year, 8,073,000 male students and 10,980,000 female students were enrolled as undergraduates. Receiving aid were 60.6% of the male students and 65.2% of the female students.